Hey guys, this is Mrs. Brookshire. We are starting chapter 9, testing claims about proportions. This first section that we will be covering, this is actually 9-1, part 1. It's on the basics of significance tests. Confidence intervals, which we studied in chapter 8, are one of the two most common methods of statistical inference. You can use a confidence interval to estimate parameters like the proportion P of all U.S. adults who exercise regularly, the true mean amount of time mean that the students at a large university spent on social media yesterday. But what if we want to test a claim about a parameter? For instance, the U.S. Bureau of Labor Statistics claims that the national unemployment rate in March 2017 was 4.5%. A citizens group suspects that the actual rate was higher. The second common method of inference is called a significance test, and this allows us to weigh the evidence in favor of or against a particular claim. And that's what we're going to be studying in this chapter, chapter 9. And we're going to be studying significance test on proportions. So a lot of these notes today, you're just going to fill in, so stop if you need to catch up, but I'm going to kind of talk you through them. But I've pretty much am just giving you them already filled in. Confidence intervals are one of the two most common types of statistical inference. Use a confidence interval when your goal is to estimate a population parameter. Like you're trying to estimate and you're trying to get that interval for a population parameter. The second type of inference, called significance tests, has a different goal, and it is to assess the evidence provided by data about some claim concerning a population. So they're going to make a claim about a proportion, or in the next chapter, they're going to make a claim about a mean. And your goal is to assess that particular parameter, okay? So a significance test or hypothesis test is a formal procedure for using observed data to decide between two competing claims, called hypotheses. The claims are usually statements about a parameter, like the population proportion or the population mean. Okay, so let's start talking about this first example, stating the hypotheses. Suppose a basketball player claimed to be an 80% free throw shooter. The player is basically claiming that his long run proportion of made free throws is P equals 0.8. This is the claim we seek evidence against. We call it the null hypothesis, abbreviated H sub O. Usually the null hypothesis is a statement of no difference. For the free throw shooter, no difference from what he claimed gives. Okay, so if we're going to have two parts of the hypotheses. Okay, so the ho, or the H sub O, sometimes we call it the ho and the ha. The ha is going to be the alternative, but the ho is P equals 0.8. Remember that this is what we're trying to claim. We don't believe it. We don't believe that that's your free throw average. The null hypothesis is the dull hypothesis, okay? The claim we hope or suspect to be true instead of the null hypothesis is called the alternative hypothesis. So we abbreviate the alternative hypothesis is H sub A, or sometimes we call it ha. So ho and ha. In this case, we suspect the player might be exaggerating, so our alternative hypothesis is that P is less than 0.8, okay? So anytime you start off with a significance test, you're always going to list what is the ho and what is the ha, what is the null hypothesis and what is the alternative hypothesis. So again, this is what we're trying to prove evidence against, and the ha is what we believe to be true, okay? So this kind of summarizes what we just said here, the definition. The null hypothesis is H of O. The alternative hypothesis is H sub A. The claim that we weigh evidence against is called the null hypothesis. The claim that we're trying to find evidence for is the alternative hypothesis. Okay, so when you have these hypotheses, you have a couple of different choices. You could have a one-sided and you could have a two-sided for your alternative. So the alternative, if one-sided, if it states that the parameter is greater than the null, or if it states that the parameter is less than, greater than or less than, if that's what your ha is, if it's less than or greater than, it's called a one one-sided hypothesis. But the alternative is two-sided if it says the parameter is different from or not equal. Okay, so that would be not equal. So if it's greater than or less than, it's one-sided, and if it's not equal, it's considered two-sided. So the null hypothesis form, it's usually like you're going to say P equals and whatever the value is, okay? And then the ha, or the alternative hypothesis, is either going to be, if it's one-sided, it's going to be less than or it's going to be greater than. And then two-sided is just not equal. So we're going to go through some rules about when you're stating this correctly, okay? To determine the correct form of ha, read the problem carefully. So you're like, well, how do I know if it's less than, greater than, or not equal to? You read the problem carefully, and it is common to refer to a significance test as one-sided, or sometimes they'll call it one-tailed, or two-sided is called two-tailed, okay? So this is what to look at when you are stating the hypothesis statements correctly. Hypotheses always refer to a population, not to a sample. Because of this, we must use the following symbols. So you're going to use mu, P for proportion or standard deviation. Usually it's either the mean or the proportion. Never use these symbols in a hypothesis statement because those are from samples. An equal sign should be used in the null hypothesis, and then greater than, less than, or not equal in the alternative. You must have the same value in both the null and the alternative hypothesis. So that number should be the same. When you're trying to find evidence either for or against the alternative hypothesis, what are you trying to, let's see, sorry, I can't read. What are you trying to find evidence either for or against is the alternative hypothesis. That's what you're trying to find evidence, either for or against. What you're claiming is the null hypothesis, okay? So the claim is the null, and then what you're trying to find evidence either for or against is the alternative. So we're going to go through and practice writing out some of these statements so you guys feel comfortable with it. Okay, so anytime you have a significance test, you are going to start off by stating the null and the alternative hypothesis, which so finally sometimes it's called the ho and the ha. Okay, in each example, define your parameter of interest and state the null, which is H sub O, H sub O, and alternative H sub A. Okay, so it says at the Hawaiian Pineapple Company, managers are interested in the size of the pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in the field after the growing season. Managers wonder if this change will affect the mean weight of the pineapples grown in the field this year. So what we're supposed to do is you're supposed to talk about what is your parameter of interest. Like what is the population that you're discussing, and then state the ho and the ha. Okay, so this one right here, it doesn't say greater than or less than, it's just that it's going to be different. Okay, they want to see if there's going to be if this irrigation system is going to make a difference. So our null hypothesis, or ho, is that the mean is 31. Okay, so that's the claim. And then the ha would be that the mean does not equal 31. Because this one doesn't say that they suspect it'll be greater than, that it'll cause more or less. They're just seeing if it'll be different. And the parameter of interest is the true mean weight in ounces of all pineapples grown in the field this year. So basically, when you do your homework, you're going to have some problems like this. And it's going to just ask you, what is the parameter of interest? So you just state what is the problem about, and then you're going to state the null and the alternative hypothesis. Okay. All right. So the next question. According to the National Sleep Foundation, 85% of teens are getting too little sleep on school nights. Janie wonders whether this result holds true in her large high school. She asked a simple random sample of 100 students at the school how much sleep they got on a typical night. In all, 75 of the students are getting less than recommended amount of sleep. Okay, so obviously the it would be P is the proportion of all students at Janie's high school who get less than 8 hours of sleep at night. And so the mean, I'm sorry, not the mean, the ho would be that P is 0.85, and she wonders whether the result holds true. It doesn't say whether, oh, I think they really get less. It says that does it hold true. So that's why you're going to use not equal. So a couple things I want you to pay attention to is, one, when you state these, the null hypothesis is always equals, okay? And then the alternative hypothesis, you just have to read the problem to see, is it greater than, is it less than, or is it not equal to? But it does always have the same value here, okay? And the null is always equals, and then the alternative is either going to be greater than, less than, or not equal to. So this one says she wonders whether it's true. So that's why we use not equal. Okay, number 3. As part of its marketing campaign for the 2010 census, the U.S. Census Bureau advertised 10 questions, 10 minutes. That's all it takes. On the census form itself, we read, the U.S. Census Bureau estimates for the average household, this form will take about 10 minutes to complete, including the time for reviewing the instructions and the answers. We suspect that the average time it takes to complete the form may be longer than advertised. So that's going to be our ha, okay? So we feel like it's going to be longer. So that's really what we're trying. The claim is, so you're going to say the HO, or the null hypothesis, is that the mean is 10. That's the claim. But we, the alternative hypothesis, believe it's going to take greater than 10 minutes. And the parameter itself is the true mean amount of time in minutes that it takes to complete the census form. Okay, so once again, you use the, the population, you use mu, and then up here we used p. These numbers are the same. This is always equals, and then that's our claim that we want to show. Okay, so you will, when you do your homework, you'll have a few of those like that. All right, so let's talk about what is a p-value. And some of you guys that have taken like, AP Sciences, you probably already know what a p-value is and have actually in experiments and things used a p-value. So statistical tests work like a court of law, innocent until proven guilty. The null hypothesis states that claim that we are seeking evidence against. So the null hypothesis states the claim that we are seeking evidence against. The probability that measures the strength of the evidence against a null hypothesis is the p-value. So that is what a p-value is. It is actually going to be a probability, and it's the measuring the strength of evidence against the null hypothesis. So we go through here, and I kind of stated what it was, and then here's the true definition written as the book writes it. The p-value of a test is the probability of getting evidence for the alternative hypothesis as strong or stronger than the observed evidence when the null hypothesis is true. The smaller the p-value, the stronger the evidence against the null hypothesis provided by the data. So the smaller the p-value is, the stronger the evidence is against the null hypothesis provided by the data. Okay? So we're going to talk about that. Like, I'm going to give you some p-values and we're going to talk about what we would do with it. This goes back to our basketball example. So in the free throw shooter activity, a player who claimed to make 80% of his free throws actually went into the gym, shot baskets, and he only made 32 out of 50, which is 0.64. In a random sample of 50 free throws, we use simulation to estimate the p-value for our free throw shooter. 3 out of 400 is 0.0075. How do we interpret this p-value? So if you look at it, this is 400 sets of 50 shots. Okay, so these are 400 attempts of 50 shots. There were only 3 sets that were less than or equal to 0.64. So your question may be, well, how could someone who claims to like have an 80% free throw average make a 0.64? Okay, so what does this say? So how do we interpret this p-value? Okay, so this is one thing that you've got to know how to do. So the way you would interpret this p-value is if the player makes 80% of his free throws in the long run. So that's what the null hypothesis is saying. if the player makes 80% of his free throws, like in the long run, over and over and over and over, many samples, there's about a 0.0075 probability of getting a sample proportion of 0.64 or less just by chance in a set of 50 shots. Okay, so that's what that p-value says. So you kind of say, hey, the null hypothesis, this is what it says. In the long run, this is what normally happens. So for this particular sample, there's about a 0.0075 probability of getting a sample proportion of 0.64 or less just by chance in a set of 50 shots. So you've got to come up with, okay, well, what does this mean? If he got a 0.64 and the probability is 0.0075, if that's his normal, well, he either had a really, really, really bad 50 shot, at the free throw line, or maybe he's exaggerating, and maybe that's not exactly true. Okay, so that p-value is going to kind of help us come up with a conclusion, and it's going to, we're going to do a couple of examples. So anytime you interpret the p-value, this is what you kind of want to say. It's kind of a fill-in-the-blank type thing. If say what the null hypothesis is, so that's what we did earlier. So if the shooter usually makes 80% free throws is true, there is we said 0.0075 chance of finding a sample with a value that is far or further from the null hypothesis. Okay, so that's kind of how you would every time state, like, what does this p-value mean? Because that's going to be a question. That's how you could state it. And it's basically just a fill-in-the-blank kind of statement. All right, so the next example says, calcium is a vital nutrient for healthy bones and teeth. The National Institute of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers aren't getting enough calcium on average. Is this true? Researchers decided to perform a test. So the null hypothesis or the claim is 1,300. They are concerned that they aren't getting enough. So that's why they use less than for the ha. Okay. Where mean is the true mean daily calcium intake in the population of teenagers. They ask a random sample of 20 teens to record their food and drink consumption for one day. The researchers then compute the calcium intake for each student. Data analysis reveals that the mean average is 1198, and there's your standard deviation. Researchers performed a significance test, and they obtained a p-value of 0.1404. Explain what it would mean for the null hypothesis to be true in this setting, and then interpret the p-value. So what it would mean if the null hypothesis was true would be, if the null hypothesis is true, then the mean daily calcium intake in the population of teenagers is 1,300 milligrams. Okay, that's pretty easy. So that's what it would mean if the null hypothesis is true. So if mu equals 1,300 is true, then the mean daily calcium intake in the population of teenagers is 1,300 milligrams. Part B, interpret the p-value. Okay, so what we would say is we're going to fill in the blank like what I told you here. So assuming that the mean daily calcium intake is 1,300 milligrams, so that's our fill in the blank, is true, there is a 0.1404 probability of finding a sample mean of 1,198 milligrams or less just by chance in a random sample of 20 teens. Okay, so this is the probability of our alternative. That's what that p-value is. It's actually the probability of our alternative. Okay. So whenever you have to give, like, what does the p-value mean? That's what you're going to say. So you're going to say, assuming that the HO is true, the null hypothesis, there is a fill in the probability, p-value, which is your probability, chance of finding a sample mean of 1,198 milligrams or less just by chance in a random sample of 20 teens. Okay, so we've kind of talked about, like, how do you set up the hypothesis statement? And we've talked about what a p-value means. Now we're going to talk about, like, we're actually going to do something with that p-value. We're going to make a conclusion with it, okay? So that's the final step. So making conclusions. The final step in performing a significance test is to draw a conclusion about the competing claims being tested. We make a decision based on the strength of the evidence in favor of the alternative hypothesis and against the null hypothesis, and that's what is being measured by the p-value. It is the strength of evidence in favor of the ha and against the ho, as measured by the p-value. All right, so how do you make a conclusion? Okay, if the p-value is small, you reject the ho and you conclude that there's convincing evidence for the ha. And you're going to write it in context. So we're going to write this, we're going to practice how to write this down. If the p-value is not small, you fail to reject the ho and conclude that there is not convincing evidence for the ha. Okay, so this wording may seem unusual at first, but it's consistent with what happens in a criminal trial. Okay, so we're going to see how to word this. There's a little thing that I learned in statistics that I say, and it's kind of weird, but you'll remember it. And it's this. So it says if the p is small. So if the p is low, reject the ho. Okay? If the p is low, reject the ho. It kind of rhymes. So that's what I remember. If you have a small p-value, you're going to reject the ho and you're going to conclude that there's convincing evidence of the ha. But if the p is not low, then you have to fail to reject the ho and conclude there is not convincing evidence for the ha. One thing that I do want you to recognize is that our conclusion is always based on the alternative hypothesis. We either say that there's convincing evidence for the alternative or there is not convincing evidence for the alternative. Okay, so we're going to practice that. All right, so let's talk about the free throw shooter activity. The estimated p-value is 0.0075. Okay, so if you think about that, that's 0.75%. That is so rare, okay? Because the p-value is small, we're going to reject the ho. The p is low, reject the ho. So what we're going to say is we have convincing evidence that the player makes fewer than 80% of his free throw, because that was the alternative, okay? So it's kind of like a two-step thing. You're going to first sentence say, because the p is low, or because the p is small, we're going to reject that. And then you're going to, the second sentence, we have convincing evidence that the player makes fewer than 80% of his free throws in the long run. Okay, let's look at the calcium. So the teen calcium study, the p-value was 0.1404. That is not low. 14% of the time is not rare. 0.7% is rare. Okay, 14% is not rare. So this one, we would not have convincing evidence that teens are, so we're going to have to, since the p-value is not small, we fail to reject it. Okay, we fail to reject it. So if the p is low, reject the ho. And if p is not so low, you fail to reject it. We don't have convincing evidence that teens are getting less than 1,300 milligrams on average per day. Okay. How small? So that's the one thing here. We just said, hey, you know, this is rare. This isn't so rare. You know, so you're like, well, how do you know what's rare and what's not rare? Okay. How small does a p-value have to be for us to reject it? You're going to be given something called the significance level most of the time. The significance level alpha is the value that we use as a boundary for deciding whether an observed result is unlikely to happen by chance alone when the null hypothesis is true. Okay, so most problems, they're going to give you an alpha. And we're going to talk about if they don't give you an alpha, you usually use alpha equals 0.05. Okay, so they're going to give you an alpha, and you're going to compare the p-value with the alpha. All right. So that's how we don't just say, oh, this is rare. Because some of you guys might have thought, hey, 14%, that's pretty rare. You know, when I'm just saying, hey, it's not that rare. 14% is not. So you're going to actually be given the significance level called alpha. And that's the value that you're going to compare your p-value with. And that's going to determine whether you reject the ho or you fail to reject it. Alpha should be stated before the data are produced. anytime you were doing an experiment, you should also have the alpha set. You don't wait until you get your data and then set your alpha. All right, let's practice a couple of these. Given a p-value. So when we use a fixed significance level alpha to draw a conclusion in a significance test, there are two possibilities. So if your p-value is less than alpha, so if your p is low, we're going to reject the ho and conclude the ha. If the p-value is greater than alpha, we're going to fail to reject the ho, and we cannot reject the ha. Okay? Or we cannot, that is not what this is supposed to say. This is supposed to say conclude. We cannot conclude. Sorry about that, guys. We cannot conclude the ha. Okay? If the p-value is less than alpha, we say the result is statistically significant in the alpha whatever it is. The three levels of significance that you see is 0.01, 0.05, 0.10. So those are usually your three levels of alpha, your normal levels. All right, so here's an example. A company has developed a new deluxe AAA battery that's supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. The company selects a simple random sample of 15 deluxe AAA batteries and uses them continually until they are completely drained. The sample mean is X bar, so this is what they get from the sample. A significance test is performed using the hypothesis. So our null hypothesis, or our HO, is that it equals 30, and the ha is that they really do last longer. That's what it says, so that's what we do greater than 30, okay? Where the mean is the true mean lifetime of the deluxe AAA batteries. The resulting p-value is 0.717. What conclusion can you make at the alpha level of 0.05? So these are the two that you are comparing. So you got to say, is this greater than 0.05 or is this less than 0.05? Well, when you compare the two, this p-value is greater than 0.05. Because the p-value is greater than 0.05, so is the p low? Remember, because if the p is low, you reject the ho. The p is not low, so we fail to reject the ho, or the null hypothesis. And so you want to say, this is how you want to state your conclusion. Because the p-value, don't say is low, just say greater than or less than whatever the alpha is, we fail to reject it, okay? So, and then the second sentence is in terms of the alternative. We do not have convincing evidence that the true mean lifetime of the company's AAA batteries is greater than 30 hours. So that is how you would make your conclusion. You want two sentences. The first sentence is you want to have the p-value compared to the alpha, so either greater than or less than. And if the p is less than, if it's greater than, 0.05, then you fail to reject it. So just remember, if the p is low, you reject the ho. But if the p is not low, you fail to reject it. And then after you say whether you're going to either reject or fail to reject, you go state the conclusion in terms of the alternative hypothesis. Be careful how you write the conclusions when the p-value is large. Never accept the ho or conclude that the ho is true. That would be like the jury in a criminal trial declaring the defendant innocent when they really mean not guilty. Because, if you ever have to be a juror in a courtroom, you don't ever say they're innocent. You just say there wasn't enough evidence to prove that they were, guilty. So we recommend that you follow the two-step structure. This is what we did here. The first sentence should give a decision about the null hypothesis, either reject it or fail to reject it based on the explicit comparison of the p-value to a stated significance level. The second sentence should provide a statement about whether or not the convincing evidence for the ha in the content of the problem. So the first sentence is, like I said, you're going to either say you reject the null hypothesis or you fail to reject and you want to have proof. So you're going to say that p is either greater than alpha or that p is less than alpha. And then the second sentence is you're going to state a conclusion and it's based on the alternative hypothesis. So if you fail to reject the hoe, you're not really saying it's true, but you just don't have enough evidence to say that the alternative. We do not have convincing evidence that the true mean lifetime of the company's AAA batteries is greater than 30 hours. Okay, so that is the first section. And that's basically for your homework. What you're going to be practicing is, stating the hypotheses, and then also given a p-value, making a conclusion. The next section is dealing with sometimes when we make a conclusion, the statistics that we have done could cause us to make an error. So we're going to talk about how that happens.